Okay, so we're going to take that information that we found in that last video and put together a sketch of each of these rational functions. Something that we ran into with polynomials is how, especially the local minimum and maximum values, we weren't finding those particular coordinates, so we needed to use a calculator to help out with that, like using a graphing calculator such as Desmos. We're going to be running into that here too. With these rational functions, there's so much behavior involved just from plotting coordinates that we can get some key features from the zeros, vertical intercept, and the two asymptotes, but really we're going to need more information. So we're going to be putting together the sketches here and really showing how the information we found comes through. But then also we're going to use Desmos graphing calculator to help fill in some blanks because it's going to be difficult to make the entire graph without more information. So let's start with those zeros. So with the x plus 1 over x squared minus 1, remember we ran into the fact that we solved for a 0 that's negative 1, 0, but when we went to find the vertical asymptote, we actually found out that we're undefined there. So what's happening here is if I have that function x plus 1 over x squared minus 1, if I factor that denominator, I have x plus 1 over an x plus 1 times x minus 1 coming from that difference of squares. And what's happening is that x plus 1, it ends up that we could simplify our rational function to be 1 over x minus 1. So it's still important to know that we have that original form because we do want to be graphing this x plus 1 over x squared minus 1, but this gives us some information in terms of the simplified form. So if I know that I'm undefined at x equals negative 1 up above there, what happens when I plug in x equals negative 1 into the simplified form? I end up with 1 over negative 1 minus 1, which is a negative 1/2. So from the simplified form, I actually have this coordinate of negative 1, negative 1/2. So when we're graphing our function, it's really going to look like the simplified form of 1 over x minus 1. However, we want to keep in mind our original form, because that's really what we're graphing. But the only difference between these two forms is going to be that coordinate, which, like I was saying before, we're creating a hole at x equals negative 1. So what I'm going to do is the fact that that 0 and that vertical asymptote lined up, I'm actually not going to have any zeros for this graph. That was not a mistake, but it was kind of extraneous information that we can't show because actually we're undefined there and we're showing a hole in the graph at this negative 1, negative 1/2. So what I'm going to do is go to that coordinate, negative 1, negative 1/2, and I'm going to draw an open circle. And then because that was the only 0 that we had solved for, that means our function actually has no zeros. We are not crossing the x-axis at all, which makes sense in regards to our horizontal asymptote being at y equals 0. So we're not crossing there. Okay, so we don't have any zeros to graph, but we have that kind of special scenario of a hole coming through. So I'm showing that with an open circle because we're going to graph all around it, but we want to show that we're undefined at that point. We have a vertical asymptote at 0, negative 1, so I'm going to plot that defined coordinate right there. We have a horizontal asymptote at y equals 0, so that tells me in the long run we're going to be getting closer and closer to 0, or getting closer and closer to the x-axis. And then vertical asymptote, so that x equals negative 1, we've covered already with that hole. It's not going to really be showing up as a vertical asymptote, but this hole is the other way that it shows up. X equals positive 1 is going to be a vertical asymptote. So with my graph right now. Like you can see, I've graphed all those important properties that I wanted to, and there's just not much on here. The idea being, I can see the two asymptotes. I have these coordinates, this hole at -1, -1/2. I have that y-intercept at 0, -1. So I get this idea that, okay, my graph is probably going to come from just below 0, go through the hole, go through that 0, -1, and then it's going to go down to -infinity as we get closer and closer to x equals +1. So I have that information here. So connecting those and going down to -infinity, we have kind of the left-hand side of our graph. Then for the right-hand side, I'm either going to be up in this upper right or this lower left. But I have no idea. I don't know. And that's where we can either use Desmos to grab some coordinates. We can start plotting some points, like look at what happens if we plug in x equals 2, x equals 3. Any of those form work. So I'm going to go ahead and show you how to use the Desmos calculator just to save us some time. So we have this x plus 1 over x squared minus 1. So there we can see that lower left that I already graphed. One thing about the Desmos calculator is it doesn't clearly show the hole in the graph, but if you navigate close to it, it'll say -1 undefined. So there is a hole in the graph there. It's just not showing it as clearly as we can by drawing it by hand. And then there's our 0, -1. We can see that vertical asymptote at x equals +1. And then from our graph, we can see we're coming from +infinity and then going to 0. So with that, I come from +infinity. Oh, let's grab a coordinate or two just to be kind of exact. Let's see, at 2, we're at a coordinate of 2, 1. So 2, 1. So I'll plot that point and just make sure we're going through it. So coming from +infinity, go through 2, 1, and then get closer and closer to 0 as we go off to x equals infinity. So that's what's going to happen with these. I'm going to need to use some format to fill in the blank for some pieces because it'll be a mystery just with these important properties. Okay, let's go to our second graph here. So x minus 1 quantity squared over 3x squared minus 1. So we had a 0 at +1, 0. So let's graph that coordinate. We have a y-intercept at 0, -1. We have a horizontal asymptote at 1/3. So I'm just going to show this as best I can. At y equals +1/3, we have a horizontal asymptote. And then vertical asymptote is ±1/√3. Let me get a decimal for that value, which is about 0.57. So I'm going to aim to be close to positive and -1/2. So -0.57, we have a vertical asymptote. +1/2, we have a vertical asymptote. So we have this teeny tiny wedge in there where we basically kind of captured our vertical intercept there. So this is gonna be an interesting one. Something I want to mention here. Well, yeah. So we graphed everything again. Huge mystery of what this is actually going to look like because we have two coordinates and then all of these asymptotes happening. Vertical asymptotes. We can never cross vertical asymptotes. That's a very strict rule because that's where our function's undefined. So like seeing this wedge between -1/2 and +1/2, and I have this coordinate 0, -1. What I'm imagining is probably something that looks kind of like a parabola down there. Like I'm going to be trapped between those two vertical restrictions. I can't cross those. Horizontal asymptotes, Again, our long run behavior, it's really more what's happening out at negative infinity and positive infinity for x, so on the left-hand side of our graph and right-hand side. In the short run, we can cross the horizontal asymptote. That's completely fine in the short run. The idea is that as we look off to the left of our graph and to the right, it's what we're approaching in the long run. We're getting closer and closer to it. But in the short run, we can cross it as many times as we need to. Okay, so this graph is a big mystery. Let's take a look at Desmos. See what's happening here. So what Desmos is showing us is we have this kind of three pieces to our function here. The first piece, so we're coming from, it looks like just above that 1/3 horizontal asymptote, and then we go towards that first vertical asymptote at about -0.58, and we're going up and off to positive infinity. Could try to grab like a rough coordinate here, like it looks like -1, +2 is a coordinate we have in here. So let's go ahead and graph -1, +2. And these are just sketches. I'm just going to use that one coordinate and show, okay, we're coming from just above y = 1/3. We're going to go and attach to that -1, +2. And then before that vertical asymptote at that -1/√3, we're going up and off to positive infinity. So there's one part of our graph. The next part is that little piece that's stuck between that -1/√3 and +1/√3. And we can see we're going through that 0, -1. You can see Desmos is marking this point of interest of a maximum at, it looks like 1/3, -2/3. So we could go ahead and graph that if we can. We might need a better scale for the graph here, but 1/3, -2/3. But basically we're coming from negative infinity. So just to the right of that vertical asymptote, we're coming from negative infinity. We're going to go up and through that 0, -1. We're going to hit that maximum point there. And then we're going to go back off to negative infinity. So it's not quite a parabola, but it's parabola-esque in terms of behavior there. All right. And then the last piece that we're looking at, so we should be going through this 0 of 1, 0. And then, so there's our 1, 0. So we're coming from, so to the right of that vertical asymptote at 1/√3, we're coming from positive infinity. And then we're going to go down and hit that 1, 0. And then it looks like we kind of bounce up out of it. And with that, we start approaching 1/3. And it looks like we're just below 1/3 as we go off to infinity. So this is a case where we are going to cross the horizontal asymptote here. So I'm going to go from positive infinity. We're going to cross the horizontal asymptote to get to that 1, 0. But then we kind of twist around, bounce up out of it, which, just to go up above here, the bounce makes sense because our 0 came from that x-1 quantity squared. So that's like what we saw with our polynomials. We have the 0 at x = +1, but it has a multiplicity of 2, and that's where the bounce comes through. So that holds true for these two in terms of how polynomials and rational functions work together. Okay, and then we're approaching that positive 1/3 from below in the long run. Okay, that's a messy one, but we just need to use a graphing calculator or grab some coordinates to help us out. Okay, our last one here. So we have no zeros for this one, so I don't have any points to plot there. We have a vertical intercept at 0, 1/4, so I'm going to graph that as best I can. We have a horizontal asymptote at y = 0. So there's our long run behavior. And then a vertical asymptote at -2. So I'm going to have a vertical line at x = -2. that we cannot cross. So this one, I have 2 asymptotes and 1 coordinate. So not a lot of information. So let's go over to Desmos and see what it's showing us. So what we see is something that looks very similar to our 1 over x squared graph. And in fact, the shape of it is exactly the same. What's happened is we've just picked it up and moved it to the left 2 spots. This is a property of graph transformations. So what's happening is on the left-hand side, we're coming from y equals 0, just above it, and then we're going through a coordinate. It's going to be a -3, +1, and then we go off to positive infinity. And that's when we get close to x equals -2. And then just to the right of x equals -2, we're going to come down from positive infinity. We're going to go through, where's our nice coordinate? -1, +1. Sorry, I meant to say, did I say that right? Yeah, -3, +1, -1, +1. Go through that vertical intercept, and then we're going to go off and get close to 0. So what's happening here? If I see my asymptotes, we're going to have -3, +1, and -1, +1. And we're going to come from just above 0, go through our coordinate, and then at that asymptote, go up and off to positive infinity. And then just to the right of the asymptote, we're going to come down from positive infinity, go through those values, and then go close to 0 in the long run. Something I want to point out is, so I talked about the multiplicity of the zeros in the numerator. Just real quick, let's talk about the multiplicity of the vertical asymptotes, because that's a thing that's happening here. So like with our first example where we grabbed that, how do I want to say this? So that x equals +1. Sorry, let's just talk about this case. My bad. So this vertical asymptote came from this x + 2 quantity squared. So notice that where we grabbed that x equals -2, that was coming from a multiplicity of 2. How that shows up in the behavior of this graph is that when we're looking at the vertical asymptote, we're going in the same direction on either side of that asymptote. The fact that we're going off to positive infinity just to the left and just to the right is coming from that multiplicity of 2. Whereas in this case, that positive 1/√3 and -1/√3, it's like if we had factored that, we'd have an x plus 1/√3 and an x times x minus 1/√3 equals 0. And solving that, we would have had our 2 solutions coming through. Those have a multiplicity of 1. And because of that, they go off in different directions. So if we're at that -1/√3, to the left of it, we're going off to positive infinity, to the right, negative infinity. So the multiplicity has a behavior effect on those vertical asymptotes. And it's coming from whether they go in the same direction to infinity or different directions to infinity.